good morning. Guess some of you were in the concert last night, so that's fine. Few people. The project text is now available both on Blackboard and Slack. There's also some attachment with some model files and one small script for our function actually for you to use if you want. So I'll try to go through some of this if I have time later today. So there's two projects. I call them Project Alpha and Beta. I list some of the interesting topics you could have for these problems, but you're free to invent your own problems. So these are just a suggestion if you don't have any ideas of yourself. There's also some common tasks for both of them, so you're supposed to answer all of these. Either or projects, and I've also written some guidelines and how I assume the communication will go, and also some tips for how to collaborate using Share LaTeX and GitHub since it's code. I've also created two new channels at Slack, so you have to join these yourself. So I will try to do all the communications through Slack, so I won't answer emails regarding the project. Because I'm sure if one of you have a question about the project, then some other will also have the same question. And I think it's more fair if everybody gets to see everything. So you're free to join both channels, it's just to keep the topics separate. So yes. And I'll try to talk a bit more about the project if I have time by the end of this lecture. Now we'll talk about convergence and stability for ODEs and PDEs. Let's see, it's the wrong one. I guess it's implicit that it's going to be for ODEs and PDEs. So this is going to be some repetition of what we had earlier with truncation errors and why we get them. So mathematical problems are often formulated in a continuous fashion. So you would have some kind of continuous area or region. In this case, it's going to be A, B. No, let's see, A over there and B over here. So we have AB, which is part of the real numbers. The thing is, these real numbers, those are continuous. And we don't have infinite amount of random access memory on our computers. Might be some revolution in a couple of years, but right now we have a finite amount of memory inside the computers, which is why we have to discretize. So we started the same, so this is going to be a point here. So you basically just discretize your interval, which means you do kind of lose information between these points. And also introduce error in your numerical simulations. So, I mean, there's been plenty of examples, but just to take a concrete one, when we are approximating the derivative of u of x, we can use the forward operator on u, or a forward differentiator operator, which looks like this: u of x divided by some h. And again, this is equal to u of x. This is by Taylor expansion, and then you will get some kind of error here, plus something. So this should be known. So we're trying to approximate this, but while doing so, we also introduce this error. And how much error we have, that depends on our approximation. how many grid points we have, and also the differentiator operator we're using. So there's a lot of stuff to actually look at there. So what's a stable ODE or PDE? So let's go over here. Basically, a stable PDE or ODE. Well, they will not explode. Meaning that the error won't accumulate in such a way that you get infinities. So phi tends to infinity. Which kind of makes sense. If it's stable, then it's going to give you a stable result. So you saw, for instance, when we were heating the steak, was that last week? Then if you didn't fulfill the stability criterion, then the simulation just broke down, meaning that it's not stable anymore. So it tended to infinity. And then we also have the concept of convergence. Which means that when solving our ODE or PDE, we want it to make sense. The ODE should make sense. So it should converge to some kind of sensible or physical result. So more simulated that the numerical solution is close to a true but often unknown solution. So should probably write this as well. So solution be close to a true. True but often unknown. True. So convergence then is closely related to stability and consistency. So for order to have convergence, you need a both stable and consistent numerical routine. So a quick example of this for ordinary differential equations. So this is an example we will look at a lot during this lecture. So we're going to use a, so for ODEs, this is too wet, nope. For ODEs, we are going to use the test problem, derivative of u with respect to t equals some general function, well, u of t, scaled by a lambda, plus some other general function g of t, with the starting condition that u of t0 equals eta, which is a pretty general ODE. So the exact solution for this, so I'm just going to mention this, is something called the Duhamel's principle. So you're not, principle. So this can always be solved on this form, eta e to the power of lambda t minus t0 plus some kind of integral from t0 to t e to the power of lambda t minus capital T g of capital T dt. And again, here we discretize the time domain. Let's see, it's going to be Tn equals n delta t, like so. So I don't suspect you will have to know how this is derived. You're supposed to know that there's a way of actually analytically solving all of these ODEs using Duhamel's principle. So then, well, what we've been looking at for most of this semester is local truncation error. So I'm going to call it LTE. Error, or LTE, since we'll be looking a lot on this. So the definition of this is that the the LTE tool is the error of the numerical, the method in a single iteration. So it will be the amount of error we do for each iteration. Or it tells us how much error it introduces in each step. So for instance, Euler's method, well, introduces a lot of errors, but as we will see later, it's actually convergent. So I'm actually going to use an example of this. So we'll be looking at how to solve this ODE using Euler's method. So again, we're looking at this ODE. I guess I should, since it's, yeah, this should be possible. So if you solve this with Euler's method, we would get that the truncation is error. So let's see, with we get the truncation error Tn d of, so d is the differentiator we're going to use, minus lambda u of Tn plus g of t. So in Euler's method, this is going to be u of Tn plus 1 minus u of Tn over this delta t minus The same here. C minus lambda u t of n minus g of t. So. And then if you can prove that this truncation error tends to 0 when this one also tends to 0, then this will be consistent. So, I guess I'll use a small space here. This is a numerical method, so num method is consistent with the equation and boundary conditions with the EQ n and BC if, well, when delta t goes to 0 of t or tau, then this should also be 0. So that means we are actually approaching the continuous case. If this delta t could actually approach 0 as much as you want, then you would have a continuous space. But we don't, so there's a lower limit to your delta t. But, well, in mathematical sense, it tends to 0. And then, as I briefly, let's see, because you have this definition. So most of this should be known by comments during the lectures. And then we have convergence. Can you read this? So this is about the global effect. Of the global effect of the local truncation error, the LTE. So, which basically means that we require that, as well as the truncation error going to 0 or tending to 0, we also want that the sum of the truncation error tends to 0. So this basically means that, I have a definition again. So if we let u of n, so this is the numerical solution, numsol, and u of t of n, this is the true solution, the true sol. Then if lim delta t equals to 0, u of big N equals u of t, where n is the total amount of steps you take, so this is going to be big T over delta t, then your method is convergent. Is, well, then it's convergent. use this later. And then, as briefly mentioned, stability is, well, also important. But in a more general sense, you can say that stability is a, well, general concept relating to how these equations behave when you do a small perturbation on them. So if you have some kind of equation, you do a small change in the input values, how does it behave? Meaning that, well, our perturbations here are the grid points. So that means that, I guess we can call this a definition again. So a stable matter depends continuously on the input values. Meaning that if you set it off with 1 or 1.0001, it should give you just a slightly different result. So you should have a continuous change. Continuously on the shell data. And then, I guess I've said this, but if your equation is consistent and stable, this means that it is convergent. Now, to actually prove this, well, quasi-equation or statement, well, we're not going to prove it, but it does make sense. So if it's consistent and stable, then it should be convergent. And also, if your numerical method converges, that means it's both stable and consistent. That does make logical sense, I hope. So you can either prove that your equation is consistent and stable and it will follow out that it's convergent, or you could prove that it's convergent directly and then you have that it's consistent and stable. So for some equations, it's easier to prove these two and then this follows. For other equations, it's easier to just prove directly that it's convergent, which is what we are going to do for Euler's method. Also, it's generally easier to prove consistency than stability. So yes. Again, we're looking at Euler's method. So, well, let's see. For Euler. So we will have n plus 1 equals u of n plus this delta t u of n plus g of t, n, like so. This is then equal to 1 plus delta t lambda u of n plus delta t g of tn. So this is the same equation we looked at earlier, which means that the local truncation error can be expressed, so it's based on this over here, u derived of tn plus 1/2. So we basically Taylor expanded this. delta t, nope, u twice derived, tn plus o delta t squared. Let's see. Delta t squared, like so. Yeah, minus this. You derived of tn, meaning that this tau n equals 1/2 delta tu twice derived of, I guess, tn, oops, tn plus some more stuff down here. Yep. So then you can easily see that as delta t approaches 0, this truncation error will vanish, because this just tends to 0 and this part tends to 0 quicker. Let's see. Which means that we have consistency. So lim delta t approaches 0, t of n equals 0, means consistent. So as you can see, that's a pretty straightforward way. But proving that it's stable is harder, fortunately. But we will do it. I'm just going to use this. Oh well. So I'm going to rewrite what I just took away. That is Tn u of Tn plus 1 minus u of Tn delta t minus lambda u of Tn plus g of Tn, isn't it? Yes. Like so. Oops. So this equation can be solved for, well, u of Tn plus 1. And we get Tn plus 1 equals 1 plus delta t lambda. Well, this is basically what's here, u of Tn. Yep. Delta t g of Tn plus delta t tau n, like so. And then if you subtract this from u of n, so now we're going to look at u n plus 1 minus the true solution, u t n plus 1. So if you remember, basically what's under here, so this is your numerical solution with only the subscript, and this is your true solution, which can be obtained with Duhamel's principle, for instance. And we would get 1 plus delta t lambda un plus c delta t g of Tn minus 1 plus delta t lambda u of Tn minus delta t g of Tn minus delta t tau n. Yep. Basically, if you say that this is En plus 1 yep. then we end up with en plus 1 equals 1 plus delta t lambda en minus delta t tau n, like so. So this is this en plus 1, or just en, this is the global error at the point n. So if this is, or if this approaches 0 or tends to 0, while our delta t also goes to 0, then our method is stable. And when it's stable and consistent, it is convergent. So then I will use this word induction. So by induction, we get that E of n equals 1 plus delta t lambda to the power of n at E0 minus delta t, some kind of sum from equals 1 to n, 1 plus delta t lambda to the power of n minus m. Then I guess there's going to be a truncation error as well, n minus 1. And so if this error is bounded, then our function is stable. So, well, I'm going to take this out of the blue, but it's true. We have that 1 plus delta t lambda is less than e to the power of delta t lambda. Kind of taken out of the blue, but it does make sense. Which means that 1 plus delta t lambda n minus m is less than e n minus m delta t, well, the absolute value of lambda. And again, this is less than e to the power of n delta t lambda. So this should hold true, since n is a larger number than n minus m. Yeah. So the thing is, here we are just getting it. So this is, I guess this is actually this is equal to e t delta lambda, where we have that, well, no, it is actually, let's see, because we have that Tn equals n delta t. So this is the amount of steps, or the maximum amount of steps. This Tn, no, this big T. That's where we stop. So I guess I can just continue here, actually. So we have that En. So the absolute value, because, well, nope, yes, plus delta t lambda to the power of, was it n? Yes, n E0 minus the sum, so delta t, this is the same sum as over here, 1 plus delta t lambda power n minus m tau m minus 1, yes. Yep. Using our inequality, we see that this should be less than e to the power of t delta, no delta, but the absolute value of this lambda constant, E0 plus, well, let's see, so this is going to be times E0 plus delta t, again the sum, tau m minus 1. So I didn't have enough space, so this is times this one, basically. And again, this is less than e t absolute value of lambda E0 plus n delta t, and the times the maximum error times the max of. So here we just say that we are going to use the maximum truncation error along our whole route. So that's why I can instead of the sum, I introduce this n, and I'm just using the maximum value because there should exist a maximal value of these truncation errors. And well, since I'm using the maximum, this should be less than this. Yep. And again, this bit here is, well, not t, but it's less than t. So, and yep, I'm going to continue over here. So right now we have that En is less than e to, let's say, t. Oop. It's the value of E0 plus t max t, yep, m minus 1. And we know that, see, the max t m minus 1 delta t t. So this is from the local truncation error, which is, yep, this one. There should be a max inside here. Yep. Well, this is actually lying a bit because now I'm neglecting this. So it's approximately not equal. So t inside our interval a, b twice. So, and we are going to say that this is just some kind of constant. So this one won't explode. So you're saying that this is C, this is the worst possible value we can have here. So just the worst. But it is some kind of constant. It is bounded. This constant C is bounded. It's less than infinity. So this is less than infinity. So combining this, we see that this En is less than T lambda E0 plus delta T big T C Yep. And then we have that, well, we can actually calculate this. This is just going to be a constant. So, I mean, this is for the first step, so this is equal to the truncation error again. These are just some kind of constants. So if you have this delta t going to 0, this will also be 0. So you see that the global error is bounded, meaning that we have a stable system. So Euler is convergent. Even though it's not the best approach, but it's convergent at least. As you've seen earlier, that you undershoot or overshoot with Euler. This is a simple method. I think that's a good way to take a break, 15 minutes.
So this is the proof for the convergence or the stability?
Say again. Oh, this is for the convergence. No. This is proof for the I think stability is going to be. Because we showed the first variable was consistent, yes.